Bombay, and Brown University, USA, and Lebanon University, Austria. He has more than 15 years of experience in the various fields of physics, like computational material science, quantum mechanical simulations. Her major research interest lies in the studies of material, in the technology, especially in the field of optoelectronics, energy storage applications, generation, environment-related problems, biomedical research of problems. She has completed successfully 4 research-funded projects under extramural research grant CSIR and 4 research grants from PhD. She has guided 7 number of PhD students under her guidance, and currently 8 students are pursuing PhD in her guidance. She has more than 70 number of research articles published in various reputed journals. With this, I welcome you again, ma'am, for the defense examination of Mr. Shantanu Kumar Naik. Mr. Naik will explain his entire research work in the thesis titled First Principle Investigation of Doped Silicon Carbide and Zinc Oxide for Optoelectronic Applications. So with this, again I welcome you and request Mr. Shantanu Naik to explain his research work. Thank you.
Thank you. Good afternoon, respected external expert here, respected faculty and my research scholar. So, myself Shantanu Kumar Naik. Today I will explain my research work on the topic of principal investigation of doped silicon carbide and zinc oxide for optoelectronic applications. Under the supervision of Dr. Pradhan Patnaik. So these are my outline of the today's presentation. Introduction, then go to the literature review. From the literature review, we find some research gap. Then from research gap, we define our objective. After the objective, go to the methodology, then result and discussion, then summary and conclusion, and the future scope, reference, application, and way one. So now introduction. Generally, semiconductor having the band gap less than 3 electron volt. But some semiconductor having the band gap that is more than 3 electron volt, known as the wide band gap semiconductor. So in our topic, we choose the silicon carbide and zinc oxide. Both are the wide band gap semiconductor having the band gap silicon carbide generally 2.3 electron volt to 3.4 electron volt, and zinc oxide is 3.3 electron volt. And several also gallium nitride, zinc sulfide, SnO2. These are also one wide band semiconductor having the band gap more than 3 electron volt. So these wide band gap semiconductors have some unique properties. Like they have the unique electronic, magnetic, and optical properties, and which properties will be best suitable for optoelectronic applications such as UV photodetectors, transparent conducting electrodes, LED, and some biological applications also. So in our topic that is of optoelectronic application, there are some desired better properties required for the optoelectronic application. These are high transparency in the UV region. High transparency in the visible region. Then high electrical conductivity and mobility required. Then suitable band gap for designing the UV and visible infrared applications. Then high thermal and chemical stability. So the wide band semiconductor generally some high performance materials which can be used in the next generation of electronic applications. Now, why choose SiC and nanotube and zinc oxide for our research work? Generally, SiC nanotube one-dimensional nanostructure which have excellent thermal and chemical stability. Then again, we can using this silicon carbide nanotube by using the band gap value, we can use in the different optoelectronic applications. Now, this also we have to introduce in the nano-range optoelectronic application. That's why we choose the SiC nanotube. Now, why we choose the zinc oxide for our calculation? So zinc oxide having a wide band gap semiconductor and high binding energy and nearly 60 mega electron volt. And also it is a environmental friendly materials. Then they have strong UV absorption and also high transparency in the visible region. Due to such unique properties, we choose silicon carbide nanotube and zinc oxide for our optoelectronic applications. Now these are some literature review. So as we choose the identical semiconductor, we choose different identical semiconductors and give what is the properties they have and what is the application they are mentioned here. Based upon the literature used, we found there some resource gap. First, we will see the insufficient verification of silicon carbide nanotube for optoelectronic application. Those silicon carbide have path number 4 already discussed. Already some properties are there, or already some research are going on. But in case of nanotube, this is insufficient verification as going on. So now, therefore, first resource gap. Second, the limited correlation between the band structure and optical activity in the doped silicon nanotube. When we go to the zinc oxide, there is a limited study of the blue three element of zinc oxide is found, and the vacancy study you see there is negligible amount of research are done regarding the vacancy study. Now, also you get the insufficient research on the most crystal effect, which we will discuss in the next after this result discussion. So depending upon this research gap, we define some objectives for our research. And these are to verify the structural, electronic and optical properties, different optical properties like absorption, reflectivity, and conductivity, transparency, dielectric function, all will discuss. For intrinsic silicon carbide nanotube as well as the metal, that is the vanadium and amended silicon carbide nanotube. Now, to verify the effect of group field of that is the boron, aluminum, gallium and indium dope zinc oxide of structural, electronic and optical properties. And after that, we increase the percentage of doping. By increasing the percentage of doping, also we also calculate the different properties, structural, electronic and the optical properties for different regions like ultraviolet region, visible region as well as the infrared region. Then after combining all the three, we have also studied the vacancy of the oxygen vacancy, then the oxygen study the oxygen vacancy and the application of the optoelectronic applications, especially the transparent conducting oxide electrode application and the UV photodetector application. Now, computational methodology. When you study first, initially you have to draw the structure by using the computational tool, that is the Material Studio. We have to create the structure by using the lattice parameter and the different atomic position. You can build the structure. After when here in the calculation, we use the Clark's principle, Energy and all the rest of the density functional theory. So in our calculation, we only consider the valence electrons only, not the correlation. Then after the construction of the structure, we will perform the geometry optimization. After the geometry optimization, for a calculation, we choose that geometry optimized structure. Then the calculation we have to perform, that is the calculation structural, electronic and optical or intrinsic silicon carbide nanotube and the zinc oxide. Then we have to verify the dope property for silicon carbide nanotube, doping with vanadium and manganese, and for zinc oxide, we will dope with the group 3 element. Then after that, we study the oxygen vacancy to verify the dopant data. Then after that, we interpret for application part, interpret for the optoelectronic devices. These are methodology. So this is the steps in the calculation. So first of all, when you cannot be predict the exact value. So we can predict the approximate value. So to that solve that exchange potential, we use the different approximations like LDA, DGA, PBE. Some hybrid approximations are there. By using this equation, we can solve a problem. That computational details. So in our calculations, all the calculations are based upon the density functional theory, and only we have to consider the valence electron for our calculation. And all the calculations are in the Clark's principle energy code. And when we calculate, for our calculation, we use the Variable Material Studio software, having the K point 1 cross 1 cross 40 for the silicon carbide nanotube with cutoff energy 340 electron volt and ultrasonic zero potential. For in case of property, all the property study for the zinc oxide and go to the zinc oxide, we have to use the K point 5 cross 5 cross 4 and the cutoff energy 340 electron volt with the ultrasonic zero potential. Now, how we get that K point and cutoff we can use that for our calculation. Similarly, also we calculate for the K point of the G cosine and